So she's an incoming assistant professor at the National University of Singapore, and her research focuses on applying machine learning and deep learning and geometry processing problems. She's currently a postdoc at the Computational Imaging Lab at Stanford University, and she obtained her PhD from Interactive Geometry Lab at ETH. She received several awards, such as Apple AI/ML Fellowship in 2020 and Swiss Postdoc Mobility Fellowship in 2022. And her doctorate dissertation also has been awarded at ETH Medal in 2022 and the best PhD thesis at Eurographics in 2023. So thanks for joining us in this workshop, and we are very excited to hear your talk. The stage is yours.
Thank you, Dina. Thank you. Thank you for inviting me. Hi, everyone. It's always fun to be the speaker right before lunch. I will try to keep this short, and let's hope you can still, enjoy Vancouver scene, food scene afterwards. So I'm Yifan. As Dina introduced, I'm currently a postdoc at Stanford in the Computational Imaging Lab, led by Professor Gordon Wetzstein. And I will be next year an assistant professor in Singapore. So that's exciting. And this is me last year at CVPR. And this is also me last year at CVPR. It's unfortunate to not be able to join CVPR this year. It's one of my favorite conferences. And I hope you all get to, take the max out of it. So my interest in research is, well, there are actually many folds. I am very interested in geometry processing with deep learning. In the last 2 years, I ventured more into the neural rendering side of it, with a goal to actually leverage 2D images as training data. And this allows us to generate 3D using more visual information. And 3D generation with AI is also going to be one of my key research direction in the future. Okay, so for today, I want to talk about geometry structures and why, especially how to use them in our deep models. So it shouldn't be strange, or these concepts that I'm going to talk about in the next few slides are going to be very familiar to the majority of audience here. So in traditional graphics, we have come up with a lot of really useful structures, starting from meshes, points. These are the classics, and they're used almost universally in the graphics pipelines. And then a little bit more kind of less used, but still very useful many times as an intermediate representation or structure would be things like voxels and octrees. And abstract up a little bit, we will have primitives, and then also key points. And sometimes, especially for deformation or articulation, we will have skeletons, and these, as you can see, gradually move into this more semantic, meaningful domain. And all of these are great examples of how we have integrated actual structures that we've been using in graphics to allow all kinds of applications. But it's very curious that actually in the recent years, in the domain of deep learning, we're seeing a trend of abolishing structures, especially if you're familiar with something with things like NERF and things like sign distance function, neural sign distance function. They are all adopting a kind of new network, it's no longer new in the world of CVPR, but in 2019 it was so this kind of let's say quite like groundbreaking sort of networks are introduced. And this kind of network are later coined to be coordinate-based network. And what it does is that instead of using a structure, it simply approximates a function that kind of just output whatever you would like it to be from some query that you put inside. And these queries are usually just points or coordinate that we sample in the space. And the output can be different things. It can be the sign distance function. And in that case, for example, the first paper that used this kind of coordinate-based network will be deep SDF. And it uses sign distance function to represent the shape. And then later briefly afterwards, we have the famous NERF paper, which represent the output of this network will be the radiance, which is composed of the RGB value of a point and the density of that point in space. And then from there is just the explosion of different types of such networks representing different signals we have in the world. And we have in the more vision side of things, we have actually semantic labels that can directly let's say label different areas in a scene, also represented no longer with a grid with points, but rather directly using this function mapping. So there's, of course, behind this, there's a reason for using such structureless network. But in this talk, I'm going to show you that even if we use such new types of network that doesn't really necessarily need a structure, I would argue that geometric structures are still very useful. And the reason are many, and some of them I list already here. And through the talk, I will be probably including even more. These reasons include such structures will actually ease the optimization challenges when we try to train these networks. And also it will provide sometimes almost for free the editing ability that we don't just get from training, overfitting or training a network without structures. And then finally, these geometry structures naturally bring more priors that we can leverage or use to make our geometry in the generation or whatever application we're focusing on more reliable and interpretable, and sometimes just more robust. So in this talk, I will focus on 3 parts of applications where we used geometry structures in different ways. And I will point at or include papers that, of course, I mostly am interested in, and maybe papers I have myself be part of, or papers that I found very interesting, especially at this CVPR, so that you can go and check them out yourselves when you have time. So let's start with the structure in the representation itself. And because I want to have this contrast of what structure can really bring you, I want to start with a structure-free representation. So like I hinted before, such structure-free representation kind of treat the neural network as a continuous function. And this continuous function can represent many things. And we mentioned that one of the things it can represent in order to encode the geometry would be sign distance function. And another popular signal to represent would be also occupancy network, occupancy signal, which means, okay, if this particular point I'm querying is occupied by some object or not. And then, so this kind of network is very popular these days for the reasons I here mentioned below. So first of all, it's very flexible compared to other representations, such as points and meshes, because they are literally, so once you have this network, it doesn't really have a limitation itself. So because this any network can basically be treated as an approximation of any function, you should be able to approximate to anything you like, theoretically, of course. And another thing is that so this function, the network is itself continuous. So the resolution of the signal you're trying to approximate theoretically is also infinite, meaning that so you can query this space as dense as you would like, and you will always get a smooth, or you will get a value out of this function you're trying to approximate with a network. And we'll see that this why I kind of try to emphasize this theoretical limitless side of it. So exactly on this note, there is, so any network, as we know, given, there is a capacity limit, let it be defined by the depth of the network or the size of parameters. There's always a cap of that representation power. And when we try to use just one network to represent the entire, let's say, shape, if we're talking about SDF or occupancy, then there's also a cap of how much detail we can, or how much, how much real representation we can encapsulate in that network. So to address this problem of the limitation of representation power, there are different kinds of spatial partitions that people use to the network, to the representation is to be able to increase how much the network can represent in practice. This is we have seen throughout the time, starting from a dense grid that just divide the space irrespective of the signal's location in the space or distribution in the space. It just divides the space into different grid and represent the signal inside the grid with some local networks. And then starting from there, we're seeing a kind of smarter or a more adaptive partition in the space, such as sparse grid and irregular grids, etc. So this is spatial partition. There are also, so what comes with it is not only the high or higher capacity the representation power, but rather that people usually desire in generation or editability, because once we anchor these representation or networks signal to some spatial domain and only describe this signal in that local region, then say if that local region also is associated with certain object, then there will be a way to actually look at that network, that specific local network, to locally change this object. We can do simple operations with such representation, such as removal, duplication, translation, and replacement. So here is a paper that came out almost 2 years ago that kind of represent a scene with so a neural field with partitioned actually dense grid, and then it learns how to mask this space with flags, whether, for example, this grid contains an object or not. And then you can move this object or move this particular grid around or remove it, mask it to be not an object, etc., so that you can kind of do different interesting things with this. Then we have, so after this partition the space, we have also other partitioning, more global partitioning. So we have partitioning of a signal into or a shape into different primitives. So for that, we have BSP network and CVX network. Both of them came at the same time, actually 3 years ago at CVPR. And they kind of encapsulate similar ideas, which is to actually represent a geometry with different convexity, different planes, so that we have a kind of compositing different planes into a convex shape. And we have also the partitioning in the frequency domain. And here I want to talk about a paper using called implicit displacement field, which came out, well, 2 years ago, or no, one year ago at iClear. So this paper, the idea is actually taken from a very well-known representation in computer graphics, which is called displacement mapping. And here you can see the displacement map is used to generate a large terrain very efficiently from just by adding, so you represent, this is a base shape, a base surface, and it can be mapped to a displacement map with a UV map. And this displacement map is just a 2D mapping with some values on it that simply tells you how far your desired surface gets extruded from your base shape. And we kind of take this idea and lift it in a 3D space. So we will have a representation for like this implicit representation that I talked about, an implicit SDF representing the base shape in 3D. And then we have also a displacement kind of nested onto the space SDF. And by compositing them together in a kind of more integral way, we'll have a composed shape, composed geometry like this. So how does it work? How do we make sure that this separation can happen automatically? So this is the interesting part. We want to be able to do the separation without knowing, okay, which part of my surface signal belongs to the base as smooth surface and which part of it is the actual details. And how do we try to do that without a supervision? The idea is to leverage some intrinsic inductive biases in the architecture of the network itself. And here what we use is a new type of activation in the network that uses sign activation. And because the sign activation has this additional parameters that control the frequency of the network, you can kind of manually define, or even you can kind of evaluate how much of a frequency a certain network actually can represent based on the these frequency hyperparameters you set in the network. So if we manage to, if we set this hyperparameter to be low for the base surface, then there is only this much frequency that the space surface can represent. So all the details will be automatically pushed to the displacement that or the details that we want to represent. And of course, these details are higher frequency, so we use a higher frequency network to with hyperparameter set to support that, to represent this detailed information. So this allows a automatic separation of smooth and detailed surface details without any human intervention. And what's cool about it is that this network is in fact very small, and we can see that the level of details is very impressive, even though this network is only contains only is only a 3 megabyte large, and the meshes itself are actually millions of vertices that takes a lot more space to even store, and not to mention the transfer. And again, similar to previously mentioned grid structure in the representation, there also comes with such networks are also, or this kind of representation partitioning in the frequency domain, we also have added editability. And in particular, what we can do is that we can transfer details that we learned from one source shape to some other target shapes that have a sort of a similar coarse shape. But say this target is a short or a pair of shorts, and it contains different folds. And by using the previous mentioned networks, we can automatically separate the details from these from the original given shorts and two pairs of different shorts in an unsupervised way. And then we can, with the method I mentioned below, somehow just transfer the details or folds that we learned from the first pair of shorts to the second one. So here, what we do is that because we need to find some kind of correspondences between these two pairs of shorts. So instead of saying, okay, this particular P is where I'm going to add this detail, I have to say this particular P actually describes a certain position in my surface, on my surface, and it should describe, for example, below the center of the waistband. And then I should be able to find the corresponding P star in the other shorts, also kind of locate at that place below the center of my waistband. So how do we do this? We can use actually learned geometry or shape descriptor to semantically to encapsulate some kind of local shape descriptor for that position P. So you can try all kinds of things here. What we tried is actually to incorporate some point net type of architecture to describe a local, the local and global position of that point in terms of in the form of a point descriptor. And then we use a 3D convolution to sort of gather that information into the sample in the space. So say have point descriptors lying on a surface, and we using 3D convolution, we can propagate this information to points away from the surface, which is let's say some point that I sample in the space. And then this will give me a pretty good descriptor telling me where I should be looking at in my original space, original shorts for that sampling or correspondence lookup. And so this is another example of how we learn to transfer such spatially variant surface details onto some new vase that itself contains some kind of detail. And when we fit this network, it learns to automatically remove that detail because of this frequency upper bound that I mentioned. And then it also learns to kind of paste the original details onto this new vase, doing this without any UV mapping correspondence establishment. So this is great. So now let's move on to the deformation part of the talk. Again, I want to start with a structure-free deformation. So in the structure-free deformation, what people usually use is some kind of deformation field, which predicts, uses a network to predict an offset to an existing vertex or point sampling. And what you see is that oftentimes, because this translation happens per vertex, and networks are intrinsically a little smooth and biased towards a lower frequency, we oftentimes see artifacts such as or distortions that are due to, for example, too many degrees of freedom, or there's just not enough regularization energy to fight any dysregularization energy that we, even if we define something something powerful, it might actually work against a perfect reconstruction energy that we want to achieve. So what do people do? Again, there are actually, this is where structures can be useful, even inside the deformation. And the first thing that actually came to be is grid. It, again, is one of the first structure people integrate when the kind of non-structure solution doesn't work. So here we have some examples of using grid or so-called lattice to actually achieve free-form deformation. And the reason why grid is the first thing people think of, or why it can be actually great, is that, so first, of course, we have 3D convolution is a direct adaptation of the success of 2D neural networks to 3D. So it's not surprising that in order to use 3D convolution, we of course need to use some kind of grid, 3D grid for the 3D convolution to operate on. But 3D convolution is actually nice in the sense that it's able to smoothen out the signals, so that we will be able to get more smooth deformation, which is actually desired in many cases. And because this same convolution kernel is able to scan through all the grids, and with some kind of pooling operation, is able to gather more global context. This is actually, or global or kind of regional context. And this is very useful to have a sort of a semantic notion in the deformation. Moving slightly away from it, we have cage-based deformation. This is different to the previous mentioned grid-based deformation, because 3D convolution is very computationally heavy. And the resolution of this of the lattices will basically have a direct impact on both the size of the network and how much detail we can capture with this the resolution. And so, in order to actually disentangle us away from this kind of resolution dilemma, we introduced a cage-based deformation. And this is, again, inspired by the great literatures, many literatures kind of in this domain, in classic deformation, that use cage-based approaches for example, interactive deformation, shape modeling, etc. So here, all these methods they are mature actually tools that are designed for deformation. So they're designed to preserve details. And so we will almost by construction not have the artifacts that I showed 2 slides earlier with distorted chair legs, etc. And then also what's quite great about this method is the cage. So the deformation parameterization is solely controlled by the cage vertices instead of the shape resolution. So we will be able, as you can see later, we'll be able to actually operate on quite topologically quite complex shapes, while keeping the network architecture as well as the capacity similar or kind of constant. So the first step is to predict the cage parameters. So given a target shape and a source shape, which we want to deform from, we first learn cage parameters that that kind of defines the cage around the initial or around the source shape. And then what we do is that we will deform this cage and then apply the classic shape-based deformation as a differential layer, which will kind of based on the deformation, based on this initial cage and the deformed shape, deform the shape lying within the cage. And as I mentioned before, there are many different ways to actually realize this deformation within the cage. And all of them are already designed in such a way to minimize geometry feature distortion. So as long as they're implementable in a differentiable way in the network, then we automatically get that power from these classic geometry processing tools. And the advantage, as I mentioned before, is that we can leverage many kinds. So here, actually, in this paper, we used one of the simpler kind just for the computational efficiency, but there are many other methods that actually focus on different types of to minimize different types of distortion. And by using this kind of structure, we can tap into that source of that great source. And then another aspect of why we want to actually neuralize this cage prediction is that by having a network exposed to different instances of chair in the data set, and having the network to satisfy all these, so the defined loss functions on all these pairs, you will force the network to kind of reason or perform well for on average, on all these paired instances. So in a way, the network will have to sort of leverage the alignment of these chairs in the data set. And as we'll see later, there is a reasoning about the correspondence that kind of just emerge from training from a data set. So how do we train this network? And we first, so again, given the source shape and the target shape, we have two standard shape encoding networks that predicts the, so in the upper branch, we predict the initial cage parameters, and in the lower branch, we predict the offset to get a deformed cage from this initial cage. And then as mentioned before, we can use standard operations in the classic cage-based deformation to deform this this enclosed shape lying within. And finally, we will get this deformed shape. And this network is supervised without any hard supervision signal by simply matching the deformed shape to the target shape by a standard chamfer distance. So basically, we can sample points on this deformed shape and sample points on target shape, and chamfer distance will try to match these set of point samples. And so this itself, without the cage structure, will actually, because it doesn't have any semantic meaningful correspondence, so there is no, let's say we didn't tell the network which point correspond to which point in the kind of deformed shape. Just by doing this alone without any cage will actually give us a very distorted deformation. But with the cage that confines the deformation space to be a very regular and kind of smooth space, this loss will no longer create any distortion. And in order to actually get a good cage, we have this penalization on the cage weights. And then also we have some additional losses to preserve the features even more. These are particularly useful when you're handling a certain type of geometry, say a man-made shape, where we want to have a flat surface to remain flat. These additional supervision or regularization can be very useful. So what can we use it for? We can use it for deforming or creating more variations of shapes so that we can have a more kind of automatic way of generation of a large stock of 3D data set. And you can see that when we compare with previous deformation method, the deformed result is much more reasonable and a lot more, I'd say, practical in the sense that they might not match this target shape as well as, for example, these vertex-based method. But I would argue that these shapes are more, they look more like chairs and cars. And another useful thing we can do with it is that we can tap in or kind of leverage the fact that these cages are not really tied to the particular vertex within itself. So you only need some global context of this the shape within. So we can once we train the network, let's say to deform a human. We can swap in this human to another kind of topologically similar, so kind of humanoid type of mesh that has a very different meshing. But because we don't care about the meshing itself, the cage only cares about the global structure. The learned deformation will still work. So you can see this skeleton can be using the same network, deformation network, without having to retrain. We can use that network to deform a new type of character. Same, for example, this robot also gets deformed to match the target poses. And there is one step, though, that we need to do. We need to be able, so because these are the human and for example, the robot or skeleton, they are different. So the initial cage need to be slightly adapted to fit that, to fit the different, so to fit this new character. So here is the optimization that we need to do beforehand, and we just need to do it once for any new character, and then the deformation will be free. So in this optimization, we basically optimize this the vertices of the initial cage so that the for a very few selected corresponding points shown at this dotted place, their cage coordinates or weights remain similar or the same, hopefully the same. And again, just to emphasize, this optimization just need to be done once, and then we can use the same initial cage that we have obtained for the subsequent deformation. And from cages, we actually, there are a lot more similar idea emerged from this kind of structured deformation. Or sort of, you can see the cage as a hybrid way to, or kind of a hybrid representation on top of, say, a mesh, a point, or even later, as I'll show, on top of an implicit field to guide the deformation. And we have, for example, using a key point to guide the cages for the deformation itself. And cages are also used directly in a trained neural radiance field. And then we have, we can use the key points, or in human body, these key points are usually referred to as joints for deforming, for example, shapes, but also deforming trained human faces or avatars, as I'll show later. And we can actually kind of build a TED mesh directly in the scene and use that TED mesh to drive the deformation itself in a user interactive way. And I just want to quickly mention this paper that is at the CVPR. It's very interesting. I just actually, I was quite I was really excited by this idea of actually starting to use dynamic dynamic information from the input. And here, what they do is that they are given a sequence of images, or given a video. They automatically learn some key points to define the motion node of in the scene. And then they're able to associate the radiance field with these key points. And then later you can kind of manually, drag these key points around to let it play, let it sort of create a dynamic of the scene. And that's very interesting. And also at the CVPR, we'll have a paper on 3D representation or for an animatable avatar directly reconstructed from a monocular video. And here there's actually two kinds of structure so before we have kind of this line of approach usually is built on either mesh, what that would be one type of structure, or not using structure at all, meaning that use some kind of implicit surface or a neural field to represent the geometry and appearance. But here we use the first point to a colored point to represent the appearance and geometry. And then we kind of tie it to a 3D 3D morphable model. And then we leverage this tied 3D morphable model to allow faster and more efficient animation. So here is an example how this can be quickly animated, and how these points actually give us a sort of interpretable geometry so that we can get the normals. We can apply different shadings on top of it. Okay, finally, I'm already a little bit over the time, so I'll go over this rather fast. I will talk about the generation part of things, which is actually the most interesting part. So here, without structure, generation, we can just generation is like tossing a dice. It kind of all depends on some randomization latent code. So the limitation is that it works really well actually on aligned data such as faces, but there is a lack of also, so it doesn't necessarily work well on human bodies, exactly because there are so much structural changes and deformations that just makes the network in networks has to model this additional deformation, which is super hard. And then of course we also don't have actual control, because all we can do is to change a latent code, and then you will just get another identity, but sometimes we just want to change the facial expression. So what people usually do, especially in the domain of body, is to incorporate parametric templates that we have developed before. The most notable ones are simple models, as well as its extensions like simple H and simple X. And for faces, we have something called Flame, which is also quite used a lot for facial modeling. And so what this model does for us is that it can allow us to generate this to let us generate the change of the human, the appearance, the shape purely in the canonical space. And then the deformation can be kind of controlled by this parametric model that we have in addition as a control input. This makes the generation much easier because we're in a confined canonical space. And actually most of the paper are operating in this canonical space. And in the CVPR, you'll see a lot of things about diffusion. And in 3D diffusion, what people do to create avatar is basically take this more kind of general idea of using 2D image diffusion for 3D, like dream fusion sort of idea, and then use an additional shape prior to enforce that shape to be more like a human. And this is again, then so here we're using either simple or flame, and we have all these kind of new concurrent papers coming out. Some of them are going to be a CVPR and some of them are archive. They're very fun, but so here the simple shapefile are used both for initialization of this, this neural field as well as regularization. And for avatars, head avatars, there's a more kind of, it's easier in a sense because because of lesser or less dramatic deformation. So people tend to either so there are actually more work that directly pans the face by optimizing the textures. So here we have clip face and dream face, for example, they're going to be introduced as SIGGRAPH, which produce really amazing results just from text prompts. And in terms of object level 3D generation, these structures are also useful. So when we have structures in object, they're usually parts, different parts. And these parts can be either learned or kind of divided in an unsupervised way. And again, I want to highlight a few papers that are coming out. The CVPR is, for example, PartNerve. And also, well, these papers are from before, but they're using sort of this leverage, they're using the data set PartNet to sort of, divide the space into different parts. And then what is even harder is the scene scale generation. And here, again, people used grid as the first idea. And but what is quite interesting and what come out this year CVPR is disco sim. And you will see that it uses bounding box to sort of look at object level neural field and then compose things together in such a way that it follows a layout prior, and it also follows through the background and foreground compositing. And finally, I want to say, come back to the original question. Why and how do we use geometry structures in this in deep learning? So the why is that these structures are great 3D priors that we can use to just improve our result. And oftentimes come together with these structures are better editability, let it be deformation or let it be kind of compositing. And finally, these structures usually, and some of it, as we have seen before, they are mature methods from the classic computer graphics literature. So there are already really good properties that we can directly use. And how do we use them? As we can see before in this talk, there are actually usually two ways. One is directly use it as sort of a hybrid representation on top of what your original representation. And another way is to use it as a sort of factorization for this for your network parameterization. And especially as a final words to folks with background in graphics, I will say that this is a great time for you all, because just look at how what are the generation results from Adobe Firefly if I give this text prompt, a girl counting 3 with her hand. This is what I get. I get 2 hands, a girl with 3 hands, 4 hands out, but in total 4 fingers, and 3 and 5. So there is generally, so diffusion model, these are all stunning results, visually amazing. However, there's just a lack of geometry and physics that currently this diffusion model or impressive AI tools are still, they seem to be quite blind in that area. So this is where our knowledge in the graphics and geometry structure can be extremely useful. Yeah, okay, so that will be all of my talk, and I look forward to questions.
Okay, thank you very much. So if there is any question from the people online, you can just write it in the chat.
Hello, can you hear me? So
Yeah.
very, very nice presentation. So I'm Dino Yang from SFU. So I'm very interested in the 3D generation question. So for the 3D generation, so for the current researches, for example, if we apply the diffusion model on the SDF grid, or people are using the tetrahedral grid to do the diffusion. So we add the noise independently on the grid or the discretization of the SDF grid. So there is, I mean, almost no 3D geometry prior through the diffusion process. So before we reach the final point of the diffusion inversion process, so all the internal process we can simply break geometries. So it is quite easy to get like broken geometries or meshes, especially topologically speaking. So I think it is for like we get more geometry prior, especially along with the diffusion process. For example, if we consider the something like geometry evolution or curvature flow, we can integrate curvature flow into the differential equation or stochastic differential equation in the diffusion process, that we can kind of guarantee mathematically that for every step of diffusion, we can get something like a valid geometry in the diffusion process.
Yeah, I think I honestly haven't thought about this, but I think you tapped on a great actually research direction, because I think the one current limitation for applying 3D diffusion for 3D types of data is that we have to kind of simulate or create the intermediate steps in a way. So if you look at the diffusion models applied to 3D, they have to build these, noisy, let's say SDF grid that kind of is not, it's intermediate representation as SDF grid, but in order for the diffusion to happen and operate on that representation, one must create these data set. And this is a very kind of cumbersome and annoying pre-processing step people have to do. But what you mentioned before is great, because you're using sort of physics and simulation to actually create these intermediate steps. And I think, yeah, this is a wonderful kind of direction to pursue. And I would think that maybe it's not, maybe it definitely has its limitation, because we cannot really get such simulation for all kinds of application. But yeah, when we, and maybe we don't have, it's not easy to get cheaply, this kind of simulation for all kinds of signal that we want to represent. But this is definitely a very exciting place to venture into.
Thank you. Thanks for your comment.
Okay, great talk. So I was wondering how to handle collision, right, using those cage-based representations. I like the fact that you mentioned hybrid representations, right? So do you think there's a potential to combine implicit representations to handle collision?
Yeah, for the cage-based deformation, there were actually there was no sort of integrated laws to penalize any penetration. And when we explored with just ShapeNet architecture or ShapeNet kind of shapes, we actually see the cage move very little. But as you pointed out later, for the articulated shapes, like the skeleton and things like that, yes, the cage will actually introduce collision. And I think, for example, the CBXNet and BSPNet that I briefly mentioned before, that uses partitioning of space, a kind of like actually implicit function in a way to represent the geometry. There is actually a very simple way, like you said, to detect collision. And I think these deformations can be hopefully combined together. Like again, we have some, for example, in a cage nerve or a deformed cage when a deformed nerve with cage paper. I think that will be a example of how different kinds of implicit and cage based deformation can be combined.
So those were the two in-person questions that jumped up. There was one.
Hello, can you hear me?
Mm-hmm.
Yeah, thank you for the talk. I just want to get your view on a few things. In particular, I think you mentioned about deformation through the cage-based like methods. But you also like kind of touch on like different types of representation. For example, the lower levels, I think the cage is more on the lower level side of deformation, like directly. You know, you build a cage on top of a mesh. Like, what do you think of like in a general setting? Is it easier or like better to do deformation through the lower level representation or like higher level representation, for example, like key points, skeletons, things like that?
Yeah, great question. I think it's really application driven, and in my opinion, I wouldn't really say cage deformation is less high level than a skeleton deformation. In fact, they are so interchangeable depending on what kind of articulation or what kind of deformation one wants to achieve. In fact, if we look at furnitures and if we want to sort of change the depth of a table, cage would be kind of a better suited proxy than skeleton. So I really think it depends on what kind of deformation we want to focus on. And then if we actually want to tackle the entire scene, there are different kinds of deformations. How do we, choose the correct node for what kind of representation to use? And I think our sort of AI assisted deformation or graphics pipeline will be kind of more systematic. It will be more like a system that you have actually a first step of choosing the right tool. Maybe that choosing itself is an AI step. And then how do we apply? So then after choosing the tool, how we can then use all these sorts of specialized method to apply that chosen tool to that specific node.
Okay. Yeah. Thank you for that answer. Also, I wondered, what do you think about like part segmentation information? I think in the end, you kind of touch upon works that are trying to model parts. Like, what do you think? Like having the part segmentation information would somehow like like be assisted for like more principled deformations or like things like that. Like, do you think these segmentation information are just like something nice to have, or is it something that's going to be critical if you really want to do let's say more fine-grained deformation or application driven? I don't know.
I think actually parts annotation is wonderful. I would use it whenever possible, because usually I think, okay, if I move back to if I have the slide about this for different part, what we essentially I think want to do is to be able to integrate whatever we came up with these automatic tools and use it in a human way. And we human actually, we have a semantic in our mind. So these labels actually, so if we don't have these labels, we will probably have shape partitioning that sort of conform in the sort of separation in the space where there might be some semantic emerging, such as left arm map to left arm, but with these labels, I think first, okay, just from this deformation quality side of things, with labels, we can have better correspondences so that we don't map, the chair handle to the right chair handle to the right side of the leg, even though they are, Euclidean space are close. But with these additional handles, we'll be able to, hopefully change just, for example, the handle of maybe just one chair, and then we can have all the handles of that similar chair changed. So I think the more kind of semantic motion we have, the easier it is to conform with our human mind to actually make the editing more kind of intuitive.
Okay. Yeah. Thank you for that. That's a great answer. Thank you.
Are there further questions, perhaps also from the Zoom audience? That's not the case. I would just thank you again for this very nice presentation. And you can put. Yes, let's first say thank you again, and then you can ask your question. Everybody who wants to go for lunch can go for lunch. But yeah, we will go to your question. Yeah, please.
Hi again. Sorry, just a quick follow-up. Do you think there are any what might be the challenge in your opinion of learning these parts in semantics and geometry models purely from data? Because there's an ample amount of data online, whether it's images or videos on YouTube. What would be the main bottleneck for learning, let's say like a model that has parts information and geometry, fine-grained geometry? Do you think it's like a multi-step thing? You first extract something, and then later on you build on like based on what you have, you further analyze it, and then have certain I don't know, like parts semantics built on top? Or is it more like learning everything, you can end-to-end learn just everything from scratch?
I think you answered your own question. I think you mapped out two different ways, and actually I would argue that there are different schools in depending on their resources. They might follow different ideas. In last year, I actually have a paper sort of trying to go to the second route, which is just trying to have one network that predicts everything. But my personal opinion or my personal take on that, it's such a network, to build such a network, we need so much data and so much, otherwise it will overfit. And it's extremely hard to train. And then so if something goes wrong, I don't know where to change. I don't know what step is missing. So my preference is actually be more kind of explicit, build things step by step. So I'm a kind of a follower of your first idea.
Thank you.
Cool. Any further questions? Otherwise, I think we should call it a win for the morning. Thanks all the speakers, thanks all the keynotes, and we will reassemble at 1:30. So please enjoy your lunch and see you all later. Thank you.
Right. Thank you very much, Yifan.
Of course.